By the end of this video, I'll expect you to be familiar with the tiny database, why we use it, and how to answer a variety of queries against it. This is the tiny database we will use to practice queries. It was carefully crafted by Professor John Carlis to be minimal in size, while also having all the shapes and patterns needed to study data modeling and database querying. We have 4 relations: creature, skill, achievement, and aspiration. As we study this data, you'll see there are many trends with exceptions. It's common to make errors in database querying by only considering the trends and forgetting the exceptions. Creatures are usually people, but not always. Kermit and Godzilla are exceptions. Creatures usually have unique names in the database, but not always. There are 2 people named Neff. Skills are usually described by 1 word, but not always. Walk on water is the exception with 3 words. Like before, the identifying descriptors are underlined with bars. Creature ID is abbreviated CID, and skill code as S code, to take up less space on the page, and because we will write them so often. Using those identifiers, we can see that creatures achieve skills and also aspire to skills. Each achievement references the CID and S code of a creature skill pair, and includes a score. So for the second row, 1E3, you might say that creature ID 1, which is Bannon, has achieved skill code E, which is swimming, with a score of 3. Aspirations also have scores, so you might say that although Bannon has achieved a gargling score of 3, he aspires to get a score of 1. Now which score is better, 3 or 1? At this point I'll reveal that score of 1 officially means good, 2 means fair, and 3 means poor. The database does not contain those meanings, so you as a user must remember that. And it's easy to forget. Without this legend, you'll probably forget at least once that the numerically largest score is 3, but the best score is 1. I could draw a boundary between information stored inside the database and information stored outside the database, such that this good, fair, poor meaning information is outside the boundary. When we store only encoded data like this, we say we're shifting the burden of remembering the meaning to the users. It's common in real databases to store encoded or simplified values in a way that forces external systems to remember what they mean. There may be performance or scalability reasons for doing this, depending on the application. If we did include the meanings in the database, it might look something like this. But officially, we'll say that this is not part of the tiny database. So later in the course, when we're programming relational algebra queries, if you're asked for good, fair, poor, you'll have to manually convert to numbers in order to complete the query. Now that we're introduced to this database, I'll give you some example queries. Number 1, who swims? Before I answer, pause here and see if you can figure it out yourself. So let's start with swim, that has the S code of E. Now how do we figure out who does that? This question is a bit fuzzy, which is to say that it's ambiguous, or it could be interpreted many different ways. We could say more specifically that if you have an achievement of swimming, then you're a swimmer. So how about if we make the query less fuzzy, more specific, and ask who has achieved swimming? Then we can scan the achievement relation for S code of E. As we scan, we can focus our eyes on the CID column and find CIDs 1, 4, 7. I encourage you to print out the tiny database and use your finger to scan the table just like that. Now we can remember those CIDs and scan the creature relation. 1, 4, 7. Creature 1 is named Bannon. Creature 4 is named Neff. And creature 7 is named Kermit. Now we have another point of ambiguity. If we say Neff, which one do we mean? Well, do we want the names or the CIDs, or both? For this exercise, let's return both, so we can make the query more specific. Find the name and ID of each creature with a swimming achievement. Notice how much more verbose we are now than where we started. The answer to this would be Bannon 1, Neff 4, Kermit 7. Now how about this? Who walks on water? You'll find that this is a superpower that no one has achieved. So the answer is that there are no creatures that match the query. That's a valid answer. More tricky one. Which people have achieved sinking? Similarly, no matches. The only creature who has achieved sinking is Godzilla, and he is not a person. What creatures have no achievements? Just by scanning the achievements table, you can notice that number 6 is missing, which refers to Carlis. Notice, once again, there is an exception to the trend built in here. Almost all creatures have an achievement, except Carlis. Another trend is that achievements usually have matching aspirations, but not always. 1A, 1A, 1E, 1E. But these don't all match. So another query is, what achievements have no matching aspiration? That is, with the same creature and same skill, ignoring whether the score matches. The one answer is the row 4A, which is an achievement but is not an aspiration. It means that Nef number 4 has achieved floating, but has never aspired to float. There are still quite a few more hidden nuggets like this we'll discover as we get to know this tiny database with more examples. At the end of this course, we'll work on the computer and execute real relational algebra queries against this data and more interesting data. Now check your understanding and try answering these queries for yourself.